Hello, and welcome to our Capstone project of the Air Force Biocontainment System. This project required a team of engineers with various backgrounds. This included Alyssa Binkowski, Marcus Mascara, Brady Baskett, Jasmine Starnes, Thomas Poloski, and Samuel Jordan. Our sponsors were Mr. Thomas Fisher, Bill Buckey, and Mark Devonish from the Air Force Lifecycle Management Center in Wright-Patterson's Air Force Base, Ohio. Our capstone mentor was Dr. Cheryl Gamillion. The Air Force often carries out medical evacuations of ill or injured patients. With the recent pandemic, they needed a new module to help contain illnesses, particularly COVID-19. Given the airborne nature of this virus, it has proven more challenging to contain. In order to carry out medical evacuation missions, it is essential to prevent the crew from being exposed, as well as keeping the interior uncontaminated to prevent the exposure to future crews. Along with this safety precaution in mind, we have to ensure our design met requirements for safe flying, medical appropriateness, and any applicable military standards. Our job was to take on the challenges of these requirements and provide a fresh outlook. The first container used to hold personnel was an Airstream trailer called the Silver Bullet. This container was designed to house Pentagon and high-ranking officials to conduct command and control tasks during transport. This container would bring the base design requirements, which all containers are designed today. The Aeromedical Biological Containment System was one of the past solutions to transport patients and was used during the Ebola outbreak in 2014. From previous designs, our clients addressed a variety of improvements which they would like to see, including a HVAC system to maintain comfort on and off the aircraft, non-porous materials for easy decontamination, and voids within walls like the standard shipping containers, which are difficult to assure all areas are disinfected. Our design consists of two parts, a main module and a utility module. The main module holds up to 12 patients, includes an anteroom for donning and doffing PPE, and is temperature controlled via built-in HVAC. The components of the module are assembled with a combination of adhesives and welding. Communication to and from the module is done via handheld transceivers or walkie-talkies. The air supply for the module is filtered by HEPA filters at all inlets and outlets. The module connects to aircraft power, but also has backup batteries that last a minimum of 24 hours. The utility module contains the batteries as well as emergency oxygen for the occupants. All components of the module have been designed to comply with the U.S. Air Force requirements for structural integrity in the event of an airplane crash. For this project, existing designs were used to generate an initial baseline. The team was provided with a wide array of documents dictating specific technical requirements and airworthiness guidelines. Using these, the team sought to produce an improved modular version of the biocontainment unit that used off-the-shelf products while still managing to adhere to the technical requirements. During the designing process, multiple concepts were generated to provide the most fundamental system of the unit. Using the guidelines and decision matrices, the team was able to narrow down the concepts that we intended to use. Modifications were decided upon. Effort went into generating 3D rendering. These models were completed using Autodesk and Autodesk Revit and contained 3D models and floor plans of the design. For the validation process, we were limited by our physical capabilities and had to substitute with other respectable means. With computer simulations, we were able to exhibit features like static loading, define the structure's margin of safety shown in the middle right, and fluid dynamics to evaluate airflow shown in the far right. However, not every aspect can be validated with a computer simulation. When testing scenarios that required participants operating the module, technical reports and bulletins would have to suffice. For example, an ingress, egress, and ditching bulletin was created to convey the appropriate testing requirements when having random participants act out an impromptu scenario where they had to quickly exit the module while under time constraints and limited visibility. Lastly, client feedback was used when identifying appropriate off-the-shelf products, like the correct kind of disinfectant, for example, one that wouldn't corrode materials within the module.